so let's remember what we were doing last time, just to quickly review. So we basically introduced numbers, right? Like what are numbers? And we introduced some notation, the Bourbaki notation, right? So there's stuff like N, Z, Q, R, right? These guys were the natural numbers, the integers, the rational numbers, the real numbers. If you're interested, we use C for the complex numbers, et cetera, et cetera. Okay, so right, we also introduced some other notation, like if I say this, if I say something like this, what does this mean? Anybody, Stella?
I think X is an element of Q, which is the rational.
Exactly. So X is an element of Q, right? That's literally what it says, and Q is of course the rational numbers. So this is basically saying X is a rational number, right? This is the translation of X is a rational number. Okay. And if I said something like this, that would mean that X is not in Q, right? This is X is not an element of Q, so X is not a rational number. Sometimes people use this notation, X is in not Q. So one puts this twiddle on top to indicate, not that set. Or sometimes people don't put it on the side, like not. The symbol means not in logic. Okay. Yeah. So we talked about these things, and we said we had this kind of odd definition, R as being all numbers that can be represented in decimal form, right? Which is kind of to me, that's kind of a bad definition, because you're defining the numbers in terms of numbers, right? So it's sort of like, this is a somewhat circular definition. But like I said last time, to actually define the real numbers is tough. We're going to sort of be very sloppy in this beginning. Okay. So okay. And at the very end, last time we made this observation, and we haven't really proven this to you, but just giving you some indication that it is true, that Q, which is the rational numbers sitting inside the real numbers, right? So the rational numbers are all real numbers. Q actually is exactly the real numbers with repeating decimal expansions. Okay, so for example, 1/2 is 0.500000000, right? It has a repeating decimal expansion, although one doesn't normally think of it that way, right? Or 1/7 is 0.142857, 142857, 142857, 142857, right? It has a repeating decimal expansion, and we saw that if you have something that has a repeating decimal expansion, you can actually turn it into a rational number, right? We saw, for example, how you would do that. Our example was something like this, right? You can turn this into, you go through some process, and it turns out that this is 12/99, right? Et cetera, et cetera. So this is the stuff we did last time. Okay, everyone all right with that? Okay, so let's go on. So that was sort of the verbal description of the numbers, or sort of somewhat of an algebraic description. It wasn't really the true algebraic description, but anyway. So we also have a sort of geometric or visual or sort of graphical representation of the real numbers, and that is the number line, right? So you've all seen this since childhood, right? This is your old friend, the number line, like your childhood pal, right? And so every, the book says, there's a one-to-one, the important thing is that there's a one-to-one correspondence between R and this number line. And what they mean by that is that every real number, so right, I've got the real numbers here, right? And so, for example, 0 is a real number, and there's and exactly 1 point here that represents that 0, right? And so to every number, there's one and exactly one number over here. There's one and exactly 1 point over here, and vice versa, right? To every point over here, there corresponds a real number, right? So this is what they mean by a one-to-one correspondence, right? It's not the case that 0 has two representations, right? Or that there are spaces here that don't correspond to numbers. Everything here corresponds to exactly one thing over here, and everything over here corresponds to exactly one thing over here, right? In the algebraic descriptions. I should have put this R over here. In fact, it already is over here. Okay. So yeah, this is what you know from your past, right? You know that these guys are called the positive numbers. The numbers on the right are right. There's that on this number line. These guys are the positives, the negatives. That that 1, 2, 3. The integers are here. The negative integers, right? Et cetera, et cetera. Right? So this is a sort of graphical representation of the numbers. It's a little bit unsatisfying because, what does this mean, right? Forget it. I'm not going to talk about it. Sorry. Last time I talked too much. This time I'm trying to restrain myself. Okay. So So graphic representation of the real numbers. Your old friend, the number line. Right? And right. So you got numbers, right? Algebraic description, geometric description, or graphical description. And we have these, our first example of relations, the greater than or less than and greater than symbols, which you're familiar with. What does this mean? If I say something like this, what does that mean? X is less than y. What does that mean? If you wanted to tell me in terms of like the number line, what does that mean? X is less than y means that in the number line, X is to the left, right? So it has this sort of geometric meaning, right? X is to the left of y, right? But if somebody couldn't see, suppose you have somebody who has no vision, right? How would you describe this relation? What would that mean? X is less than y. There's you can also talk about it algebraically, right? That y minus x is positive, right? Y minus x is positive. That's one way of saying it. And similarly, right, if x is greater than y, that would mean that x minus y is positive. Right. So you can define these things in multiple ways, and this is something that we'll see often in the course. That you can understand things and you can think about things in entirely different ways. Okay. So this is how you see it as a visual person, right? But this is, suppose somebody who doesn't have vision, right? I've seen blind mathematicians before. I've met blind mathematicians before. Okay, right. Yeah, in fact, one of the craziest counterexamples in topology is something called Alexander's horn sphere. I suggest you look it up. It's this wild visual thing, and that was created by blind French mathematician, as I recall. That might be wrong. Okay. 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 So yeah, so relations. Right? If numbers are nouns, then relations are maybe verbs. Okay. Next thing that we want to talk about is just some more notation. So interval notation. So this is just it's just something very basic that we need to know. So probably you are familiar with this. So if I have two numbers, x, a and b, so let's say we have a and b, and a is less than b, then if I write something like this, a comma b, what does that mean? What does that mean? A comma b, square brackets. Anybody know? You should know. If you read the book, you know. Yes, Isa.
That it includes A and B.
What includes A and B? The interval, right? Yeah. So this describes an interval, right? So let's say that A is here and B is here, right? Then, right? What this thing is the it's from A. It means all numbers between A and B, but also including A and also including B, right? So this is geometrically what this notation means. Okay, right. So if I write 0, 3, right? That would mean all numbers from 0 to 3 inclusive, right? And we use the solid dot to indicate that it includes the endpoints. If we don't want it to include the endpoints, then we use the circle here, an open circle. We fill it in, it includes that point. Okay. So we could also describe this more algebraically. So again, what if the person can't see, right? Like what does that mean? Well, you can describe it more graphically, more algebraically by saying, well, this is the set of points x that are in the real numbers, where x is greater than or equal to a, and x is less than or equal to b. Right. So this is the same thing as this picture here. Okay. So just to start getting familiar, if you're not already, with set notation. Right. So let me read this in English. Right. The set of all real numbers for which so let me say this, which are less than or equal to b, and greater than or equal to a. Let me also say that this is a little bit clumsy. So mathematicians would usually say something like all real numbers x such that x is less than or equal to b and x is greater than or equal to a. So we usually you'll see people use this phrase such that. Okay, such that means basically with the property that. Okay, with the property that. Does this make sense to people? Anybody confused by this? Okay. Okay. And of course, normally we abbreviate this as just one statement like that. Yeah, x lies between a and b inclusive. Okay. Take a minute and write down what this should be as a picture and also what it should be as in set notation. So see if you can write that down. So this is the so-called open interval. Right. This is the closed. These guys are called closed intervals because they include their endpoints. Okay, turn to somebody nearby and say, this is what I wrote. Show them what you wrote, or talk with them. Talk with somebody for a minute. Okay, so the picture is, right, it's the same thing as before, but you use the open circles rather than the filled in circles, right? And as a set, does somebody want to say what you said? Maybe it's yes, please.
A less than x,
Okay, so yeah, but you need to say like the set of all x that are real numbers where that satisfy. You can think of this as that satisfy mark. So like the set of all x in R that satisfy this relation. Okay, so you got to have this left-hand side. Otherwise, the right-hand side doesn't really make sense because like it's a set of what? This relation? You know, you're sort of like you're putting the adjective in, but you have no subject. Okay, and notice that this x doesn't really matter. I could have called this, the set of all z in R, right? Everything in R that lies between A and B, right? So yeah, I could call this whatever. This is just a dummy variable. Okay, is that all right? Right. Okay. Okay. Other kinds. So closed interval, open interval. You can have half open, half closed intervals, right? If I say something like this, then that would mean, right, the set of all x that lie so that it's greater than or equal to A and strictly less than B, right? So half it closed on the left side, open on the right side. It should not be clear to you why we care about these things. It's simply that they're going to occur a lot in the course, so we might as well introduce them. Okay. Last kind of interval we're going to talk about is infinite intervals. And this is just a notation, let's say. Okay, so this notation is going to involve the symbol infinity. In the book, it says there is no number called infinity. Okay, we're just using it as a notation. Okay, so you don't want to think what is 1 plus infinity. Okay, infinity at this point is not a number. Okay, if you go on into higher math, then actually infinity is a number. Okay, but right now infinity is not a number. Okay, so if you go into complex analysis, complex math, complex numbers and stuff, infinity actually turns out to be something cool. The top of a sphere, the point, like the North Pole on top of a sphere. But right now, infinity doesn't. We're just using infinity as an abbreviation. Okay. So it's just an abbreviation. So if I say something like a comma infinity, and you don't include infinity because you can't, right? Infinity is not a number, so you can't include infinity in your set. If you say something like this, what it means is that you're starting from A and you're going on for the rest of the number line. Okay. So in other words, it's all real numbers that are greater than A. And there's no upper bound placed. There's no constraint placed on how big it is. Okay, right. If I said negative infinity, positive infinity, no. If I say negative infinity A open, well, you can guess that's going to be A, but not inclusive, and everything going back to the left of the number line. Right. Yes.
Why A less than
X is greater than A. It's everything greater than A. Right. So what this means is that what this notation simply means you want all points that thank you. That's what you're asking about. Not the greater, but why not equal? Yeah, thank you. Okay. So this one would be X is less than 3. Right? And if I wrote something like negative infinity, positive infinity, well, that would be all x in R, but then no constraint on the left and no constraint on the right. Right? So this is just all of R. Right? It's all points in R such that no constraint. So it's all points in R. All real numbers. Okay, so that's the notation. Okay, so everybody okay with that? Like I said, did I tell you I can't see very well? Yeah, I can't see very well. So I find that if I open my eyes really wide, I can see a little bit better. So if I'm like this, it's because I can see, it looks kind of ridiculous, but anyway. I can focus on you a little bit better. The cloud, maybe I'm not sure, like the cloud is less if I open my eyes bigger.
But that doesn't affect your short distance, like you're able to write.
Yeah. So it's just that there's this kind of milkiness, like a slight milkiness in front of my vision, and it's not everywhere. It's here and there, and sort of like. But if I open my eyes really wide, it doesn't work all the time. But it's not that serious. It's I don't know if your parents are old enough to complain about floaters in their eyes. So things that like there's these like clumps of cell that break off from the back of your eye and start floating around in your eye. This is just a more extreme version of that. There's like lots of floaters in my eye. Eyes. Okay. Section 1.2, absolute value. Okay, so the first section was on really fundamental stuff, like what are numbers, these sort of basic things. And then we did go to section 1.2, absolute value. So you can imagine that absolute value is also really a fundamental idea. Yeah, and the point is that numbers basically have two qualities, two sort of like defining qualities. The first is the sign, right? If it's plus or minus, and then the second is the size, right? The magnitude. The magnitude of the number, right? Like how large it is, right? So, right? Every number, if I look at 5, say, right, it has a sign and then it has a size to it, right? So these are, and this magnitude is we describe it with this function called the absolute value function. Okay, so you can see that these are really, absolute value is something very fundamental about the numbers. Okay, so let's define the absolute value function. So for a real number x, first definition, and this is going to be a geometric definition. This symbol denotes the distance of x from 0. Right? So, like geometrically, you measure the distance of that thing from 0, and that's what you call the absolute value. The distance of x from 0. Okay, that's kind of it's kind of an unsatisfactory definition because it's very, it sort of relies on other notions. But in any case, the algebraic definition, this is maybe the more formal definition. The absolute value of x is defined to be, so this thing is read the absolute value of x. The absolute value of x is defined to be, notice this I've introduced a new symbol, is defined as, well, it's defined as x if x is greater than or equal to 0, and it's defined as negative x if x is less than or equal to 0. Okay. So this is the more, I'd say this is the more formal definition. Okay, so so for example, right, if I say, what is the absolute value of 10? What's the absolute value of 10? Why is it 10? Well, you could go back to the definition and you say, I think let's go back to the algebraic definition. You say, the absolute value is defined to be, you have to look at the input. If the input is bigger than 0, then it's just the number itself, right? So this is going to be 10, since 10 is bigger than 0, right? And if I said, what's the absolute value of negative 10? You would say, well, it's going to be negative 10, right? In other words, positive 10, since 10 is less than equal to 0. Negative 10 is less than equal to 0, right? Okay.
Professor?
Yes.
I'm a bit confused on
Yeah.
why we wrote that negative x. We say negative x if x is less than or equal to 0.
Yeah.
Like, let's say it is 0, then
Yeah.
why is it negative x?
It will be because negative 0 is still 0.
Oh, I see.
Yeah. So, yeah, you know, yeah, I'm glad you pointed it out that actually you could do it either way, right? If x is 0, you could either take this definition or you take this definition. It's okay because in this case you'll get 0, in this case you get negative 0, but negative 0 is 0.
0.
So it doesn't
Cool.
matter. Yeah.
Awesome.
Yeah, thank you. Yeah, yeah, yeah. You're right to be a little bit, to complain a little bit about that. Okay, so so that's the first example. Second, if x is greater than or equal to 5, what is the absolute value of x minus 5? Take 30 seconds and write something down. And if you want, you can do the second part. What is absolute value of 5 minus x? Okay, turn to somebody nearby and tell them what you wrote down. Prisa.
Is it asking if it's negative or positive, or is it asking for like the absolute value?
It's asking what is this, just like over here, what was this, right? What is the absolute value of 10? Well, it's 10. What is the absolute value of x minus 5? It's, what? Somebody tell me? Isa? Negative x minus 5?
Or like just negative x minus 5. Like it's
Negative x minus 5?
Yeah.
Okay. Other possibilities? Yes, please.
Just
X
x minus 5.
minus 5? Okay. Anybody else?
I mean, you can
Is
also
it-
say 5 minus x.
5 minus x? Oh, you mean, in that case, you do mean,
Right?
in that case, you do mean, I think, negative
Oh.
quantity x minus 5, because that would be,
Yeah.
that would be
No,
5
you're
minus
right,
x.
yeah.
Okay,
Gotcha.
yeah, okay. Okay, so in the interest of time, let me just say that, so let's think of how we would figure this out. You would say, well, what is this? Well, let's go back to the definition. right? The definition says you have to figure out if the input is positive or negative, right? Because if the input is positive, it's going to be x. If the input is negative, it's negative x, right? So is this thing positive or negative? It's positive, right? It's positive because x is bigger than, x is on the right side of 5, so x minus 5 is positive, right? So this thing is positive, and so the answer is x, right? I'm sorry, the answer is it itself, right? It's going to be x minus 5, right? Since x minus 5 is positive, right? Okay, and then over here, what would the answer be, Isa?
Then it would be negative 5 minus 1.
Yes, so it'd be negative quantity 5 minus x,
Yeah.
right? Because, and why? Because 5 minus x is negative, right? Because x is on the right-hand side. So, right, so since 5 minus x is negative, right, then the output, the function says, oh, you gave me something negative, I'm going to return to you the negative of that, right? So it returns this, so it returns x minus 5. Okay. Okay. So I know this seems kind of pedantic, but this is the way that you want to think about it, actually. You want to think this absolute value function is something like a machine, and you want to say, it says, what do you give me? If it's positive, I'll give you the same thing back. If it's negative, I'll give you negative what you gave me, right? So here, it's like, oh, you gave me something negative. I'm gonna multiply that by -1 and return it to you. Okay. Last example, say x is in 1, 2. What is absolute value of x minus 1 plus the absolute value of x minus 2? I had one more example, which was if x is less than 0, what's absolute value of negative x? If you have time, you can try that. Okay, we're running a little bit over time, so let me just run through these myself. Sorry. So let's think, right? If I'm looking at this expression, well, I've got x minus 1. So I think, okay, the absolute value function says, tell me if it's if you give me something positive, I'll give it back to you. So you say, oh look, x minus 1 is positive, right? Right? X lies between 1 and 2, so x minus 1 is positive. Right? So the absolute value function is going to look at that and say, okay, it was positive. I'm just going to give it right back to you. Okay. Then, second part, x minus 2, well, that's negative, right? Because x is to the left, right? So x minus 2 is negative, so the absolute value function is going to return negative that. Right? Okay, and if you work it out, you see that you get x minus 1 minus x plus 2. Right? In other words, you get the x and the minus x, they cancel off. You get 2 minus 1, which is 1. Okay, so the answer is 1. Okay. Second one, you'd say, okay, well, is the input positive or negative? Well, x is negative, so negative x is positive. So the absolute value function is just going to return negative x. right? This thing that you fed into it was positive. The absolute value function says, oh, you gave me something positive, I return it to you. It's like a human being. You give me something nice, I'll give you something nice. If you give me something nasty, I'm going to give the same thing back to you. Hopefully that's not human beings. But sometimes it is. Okay. Any questions on the first one? Everybody understand the first one? Okay. Let's stop here. If anybody has questions about it, please come up, and if you can stick around a little, come up. Let's stop here for today.